So we come out into here. So in that case, we will not see the top of the white pants. We only get the bottom of it. That's the first thing we do. But then there are so many white dots. And it could be other things with white, right? So one thing we do is that once we create a mask for the white, which is for the value, the brightness of the contrast, we get a lot of white areas. The first thing we do is make sure the white area need to be greater than certain size, like greater than 500 pixels in total size to be considered. Yeah, so these are already out of the picture when you put the size. And then the other thing there could be something else. Maybe there's another tile here that are in the camera. What we do? So what we do, another thing we do is like we expect we're going to see our target here. And if the other tile Y is too far away, we do not consider that. So they put in another check. And then how are we going to determine this dot? Good question.
I have a question. What if you see two stacks? Then you're seeing two of the white lines and two of the...
Yeah, that's what I said. If there's another tile here,
Yeah.
then because what we do is we expect our robot to be at most off by say 3 inches. So
you're
on
most likely
each
not going to
side.
see it.
On each side.
on each
So
side.
you have the error counted.
So that so we expect to see the white around here, like
I see it.
around here. And if the white you see is too far away from what our expectation, do not consider it. So in the end, if lucky, if you move within the certain, we say you have to move certain distance from the white stack. Cannot be too far, cannot be too close. Otherwise, so what we do is like when we too close, it's like this. When it's too far, it's like this, and this is right in the middle. So we want to aim to shoot at this place. But then if even we are off by 2 inches too far or 2 inches too close, we still see that. So in the movement to close the pixel, we allow total minus -2 inch error to be allowed to see this correctly. And we say we are within 3 inch.
So this whole program was meant to just mitigate the possible deviation between our robots autonomous getting back to the white stack.
Yes.
Okay.
So what does it do if it realizes it's off? Does it just keep
Then
going?
then we just keep going, just like what we did before.
Just keeps going. It doesn't like stray for it. Just keeps
Doesn't
going.
correct. We
I see.
do not do correction. Just like
So
if
this
we
is-
don't see it, then we just keep going. Now, okay, I didn't see anything. Maybe some other problem, but we'll be just acting like what we had last week.
This is so. Can we like if something goes wrong? Can we check? Do we have access to these like photos after check it?
Yes,
Yes.
this is from the capture. So after
So
the
if something goes wrong, we can like adjust it or something. Or, like,
Yeah, it's all in the log
figure it
file.
out.
It's all in the log files.
it's in the photo is saved.
How like quickly does it do the contrasting and all that stuff and the cropping? Is it really fast?
Oh, so the whole thing
Instant.
is done within 100 milliseconds.
Oh, so it's really quick.
You stop, take a picture, and then you go.
Okay.
It's very fast. But the program does allow them to put in up to 500 millisecond delay. But when we watch the log file, 100 millisecond is enough so we can move on.
So, sorry, you go ahead. It's taking the picture while it's moving, right?
We stop first.
It stops.
Okay.
We stop and then we start to look. It takes some 100 milliseconds, then we move on.
Right.
So now we see the dot. How do we see the dot? So now because like if you it's hidden here, right? Last year what we do is like we use the mask. So here we use a mask based on the value of the brightness, the value. HSVV is the value. So when we see the brightest white area, what you get is what's they call a series of dots. And previously, what we usually do is just get the bounding rectangle. So that's how we do with the team element. We do a bounding rectangle of the area. Then you say, okay, the whole bounding rectangle, the center is left or middle or right. That's how we do the team element. Here, bounding rectangle is no good because what I want to see is this dot, right? That's the good, and you don't want to see here doesn't count. You want to see this dot, the center of this, because this is consistent. So what we do is, so instead of like using bounding rectangle, we consider all the dots in this the result in the mask. Contour, and then only the dots closer to the minimum path of the bounding rectangle. Like so, this is bounding rectangle. Only the dots within the bottom 5 points of bounding rectangle we consider, and then get the mean and max of the x, and then the center is what we want. So that's how we get the red dot every time here. So now we get the red dot, which is considered as like the x on the image and y on the image.
Is it red and blue or is it just red?
There's no real dot.
We draw it there.
I know. I'm just saying. I'm just curious. Is the red one for the red alliance or is it just
Christopher,
Christopher,
there's no real dot.
he's just doing for you.
Oh.
It's an imaginary dot.
It's an imaginary dot. It's just white tape.
He's just
There's
saying,
no-
at the end of the
there's no
day,
actual dot.
the robot knows it's there. That spot,
I
it
draw
knows.
it up
Yeah.
to see.
That's the bullseye.
No, but it's not really a dot.
Oh, but like the robot isn't doing the dot. He just showed that. Just
It knows that position. That's
It's-
all he's saying.
It's for discussion purposes.
Yeah,
Okay.
it's
Yeah.
for the programmers.
I save the image. When I save the image, I save the point where I see the x is,
okay.
where I see the center is. So if there's another pile of white here, I would draw a dot there, but it's a green. Say this is. I see the dot, but I don't consider it. I draw a green dot on. If you see 2 piles, you can see a green dot.
Yeah, and guys, this is all done with OpenCV. It's just part of the standard software packages.
That's like the river path.
Yes.
And Christopher, one thing is, Christopher, you observed the fact that last year, the mat that they actually had on the field was white. So where you see the carpet there, that could be all white, and it still will work.
Yeah, exactly. Okay, so now if we see the dot, how do I translate that into how much we are off, right? And that's why I put 2 dots on each side. They are 2 inch each onto the picture. And then so the whole idea is see like, okay, this is ideal. I want to see that ideal here for this distance. This is ideal. And then, but if when the robot get to the field, I see the pixel here. How much do I know is away, right? How far? This is what I see instead of the one that I have already captured before. How much am I off? So what I do is, this is all x, y on the image, and what I see is I use a tool to measure how many pixels from here to here, how many pixels from here to here. So based on these 3 pictures, right? So this is the one that is ideal. Then this is 2 inch farther away. This is 2 inch too close. I capture 1, 2, 3, 4, 5, 15 positions, and put them into a spreadsheet.
So guys, he's using the photo with a known distance as a ruler, right? Because when you take a picture, you don't have scale.
He can use the pixels because he knows the scale.
For calibration within the program.
So
The pixel you mentioned is image pixel, not
Not the game.
our game. Yeah.
So when I have these pixels, I have like the 2 on the outside, the closer, the center dot, and 2 on the right side. Then I can note down the x position, y position of it. So as you can see, this is 2 inch from here. This is 2 inch from here. So when is this one is the one that is the ideal center one, and this is 2 inch too close, this is 2 inch too far. And then what I do is I say, okay, how many pixels per inch? It's about 33 pixels, 35 pixels, 38 pixels, very close. So even I just use the middle one, it's great enough. But it's like you're off by a quarter or less than a quarter inch, the robot will pick it up. So it's pretty good. But let's just try to be optimal. So what I do is I even say, first I want to see how far did I make it to the optimal distance, the closer to the white from the x standpoint. So I look at is like how far what's the y position of the image closer to me. So that is this part, right? As you can see, if I get too close, this too close to the white, let's see, it increases. When I get further away, the white is decreases. So I use this to judge the distance from the robot to the wall. Because as you get closer, the white will become get closer into the bottom of the image. So that's one consideration. Once I do that, I can guess how much I am closer to the pixel. And the same map, I do the X. I just do the map here, and then I can guess which row I should use to determine the X position. So then I know once I go through this similar map, I can know, okay, I am, say, how many inch from the red dot, how many inch I'm off the center of the white dot. And then adjust the robot position to catch it. Why I have to do this?
So you are actually adjusting the robot position?
Yes. So that I update the current position of robot. So robot position is measured by row runner.
I see. So it's still not shifting the robot's position.
Yeah, update the existing position. I mean, in the memory. Say,
But
the
would
row
you
runner.
want to make it go to the right spot? That way it finishes the
So,
rest.
No.
so Christopher, I know some of them, Hayden's done this quite a bit with this, right? So in Roadrunner, you have destinations.
Oh, so it just goes through this.
So it uses this, so let's say the program is going for a destination, right? So it's got a target already, and the computer's thinking it's got a target, it's using the dead wheels for that. Remember, the computer doesn't know where it's at, it's just using the dead wheels for its direction. So when you use the camera, you see where the pile actually is. Again, you've got accumulation of error, and so it goes, oh, the pile is actually over an inch. So I adjust my destination target on the fly. So instead of going to position, x equals 15, I need to go x equals 14. So it just adjusts.
Little bit off. Now, actually, what I see is like when you use runners, and let's go for 100 inch and go left by 5 inches. You do you go.
Great.
At the end, the runner say, okay, now I'm what you want, 100 inch forward, 5 inch left. And take a look. Oh, you're wrong. Actually, you only forward 98 inches, and then you left by 2 inches only. And update the current location, current coordinate. So the pile did not move, but I update my current
Where the robot thinks it is.
what thing you are. Because if you update the target, then the rest of the route has to change. But if I update where I am at to the correct position, then the rest of the route will not need to change.
Target stays the same, just updates the position.
Yeah. So any
To make
questions?
it easier, no need to change the robot position, like adjusting. That would be very time consuming and
Because you have to calculate all the routes otherwise. So if I update myself, then the rest of the route that I could calculate it, I don't need to touch.
Yeah. And it should make your return more accurate too.
exactly in the future, all the future path is more accurate because we correct in the middle, some part in the whole.
So this is not the best way I would like to do. So because it's not exactly linear. I mean, I'm just for the area you're looking at, the small amount is linear. But when you're looking, this doesn't apply to the whole map. I mean, if you use the whole picture to use this, it's a totally different map. But
It crops it, right?
because it's all angles, how much angle you see it.
Who's done photography? They know the lens distortion right as you get
Yeah, it's
further out.
perspective, right? Yeah.
Yeah, so this is just
And remember,
simplified version.
even with this one, our camera is not straight in the center of our robot, it's off to the side.
It's like hot glue down.
Yeah.
So
Yeah,
that makes
so
it difficult, right?
That's
Impossible to
what makes it
calculate.
difficult.
Yeah.
If the
And also, you don't know, like, the robots, it's really hard to get perfectly parallel.
yeah. So
Getting
so
the
this is
camera perfectly
what we do
90
is
degrees.
assume the robot is parallel. The robot is off by 1 degree, still work, but if robot
Yeah,
by
it's
50
off.
degrees, it's gonna be off. So yeah, the theory is that if the robot had the camera in the center and look forward straight, all this will be much simplified. We have no choice but to use this kind of
Yeah, in the future, if you guys work in the same field, if you want to do this for the surgery or anything, you can use this this method. You have to use the original, the angle one. But our game, it's much easier. It's okay to have 1 inch difference when we pick up the.
It's great.